So let's do an example problem for average atomic mass. This is question number 1 on the average atomic mass problems number 4 page, I believe, that I gave you for practice. We'll go through number 1 together. 2, 3, and 4 are very similar. I'll probably ask you to work on those in class. And then the other type of average atomic mass problem will be coming up in the next video. It's a little bit different approach to the same equation, solving for something different. It takes a little more math to work through, but we'll start with these first, then we'll go through those next. So our first type of problem here takes a question like number 1 and asks the two types, or tells you that the two types, isotopes rather, of iridium are listed below, each with its percent abundance and the composition of its nucleus. Now, hold on a second. Why are we just talking about the nucleus? Well, remember that for average atomic mass, we only consider the subatomic particles that have a significant mass that actually count toward the mass of the atom. Remember, the 3 subatomic particles are protons, neutrons, and electrons, and that electron's mass is very, very small. So small that we don't usually count it toward the atom's overall mass. So in this case, the nucleus, which is the protons and neutrons, are the only particles that count within the atom toward its mass. So in this question, we don't count electrons in any way. It says, using the data, calculate the average atomic mass of iridium. So the question gives us 2 isotopes, and the circles there represent the nucleus, nuclei of the 2 isotopes of iridium. In this case, it says the first isotope contains 77 protons and 114 neutrons. The second isotope contains 77 protons again and 116 neutrons. So notice both isotopes contain the same 77 protons because that's iridium's atomic number. Take a quick glance at your periodic table. Remind yourselves that right here in the middle there, 77 for iridium, that atomic number tells us that every iridium atom, no matter what the mass, will have 77 protons each. And so in this example, that's exactly the case. 114 neutrons, 116 neutrons in the 2 different isotopes. And right below that it says that we have 2 different kinds by name. We call them iridium 191, which is that 77 protons plus 114 neutrons. And we have iridium 193, which is 77 protons plus 116 neutrons. Those 2 additional neutrons give us 2 additional AMUs toward the iridium's overall mass. So the second one is 2 AMUs heavier. And then the percentages given there tell us that that first isotope, in all the universe, we think iridium is found to be 37.30% iridium 191, that isotope. And then the slightly heavier one, iridium 193, makes up the other 62.70% of all the iridiums in the world. Think about it kind of like a pie chart, if you will. We could divide the pie into 2 parts, iridium 191, which is 37.3%, and iridium 193, which is the other 62.7%. It's kind of a pie chart, if you will, if that helps you to think about it. Now, to find the average atomic mass, I need the equation that I just told you about, and it's there on the right side of the screen here. The 2 isotopes times their percent abundances written as decimals. So we're going to go through that together, and I'll work you through this problem. So I'm going to shorten up average atomic mass. Instead of rewriting that every time, I'm going to go ahead and abbreviate it as AAM. And my average atomic mass will be the mass of the first isotope. Well, here the first isotope is iridium 191. So I'm going to bring that 191 down, AMUs, times its percent abundance written as a decimal. So this percent abundance, 37.30%, will come down and become a decimal here, 0.3730. Remember, we simply move the decimal point over twice. And if you do that over here, you can kind of show it. We get 0.3730. Plus, the equation says, plus the mass of the second isotope, which is iridium 193, so 193 AMUs, times its percent abundance as a decimal. And that percent abundance here again is 62.70%. We're going to bring that down over here and write it as a decimal, 0.6270. Remember, I said before that the 2 percentages should add up to 100 and the 2 decimals should add up to 1. And if you check, these do. All right, so to go ahead and solve this now, we're going to take each of those masses times those percentages and get answers for each of them first, because we want to consider the rules of significant figures. So we're going to multiply 191 times 0.3730. I'm going to get my calculator here. 191 times 0.3730. Now my answer comes out as 71.243. How do I want to round that off? Well, remember the rules say that when multiplying, the answer should have as many decimal places, the answer should have as many significant figures as the original value with the fewest significant figures. Well, 191 has 3 significant figures, And 0.3730 has how many? Hopefully you look at that and you count 4 significant figures. The decimal point is present, so we count from the left side, starting with the first non-zero, 3730. Those are all precise, so 4 significant figures. My answer, when I multiply those together, should have 3 significant figures, because 191 has only 3. So how can I round this answer off to give me 3 significant figures? 71.243, as it's written, has 5. Let's round that off to have just 3, and we get 71.2. So I'm going to bring that answer in and write it in as 71.2 AMUs. Now that's not my final answer, that's just this first part, right? This first pair. Plus, we need to multiply our second pair. So 193 times 0.6270. And the calculator says 121.011. Now that answer has 6 significant figures in it. We can't have 6. 193 AMUs has just 3 again, and 0.6270 has 4 again. So our answer can only have 3, the fewer of those 2, remember? And so 193 times 0.6270 gives me an answer of, when rounded off to have 3 significant figures, 121 AMUs, right? So we're going to take the 121.011 and round it off to get 121 AMUs. 3 significant figures in each of these. Now, when adding those together to get our final answer for this problem, we're going to add those together. And remember that the rule says that the final answer should have as many decimal places when adding as the original value with the fewest decimal places. Well, 71.2 has 1 decimal place. 121 has no decimal places, so my answer can only have, well, 0 decimal places. It can't have any. So let's go back to our calculator and take 71.2 when we've rounded it off, plus 121 rounded off, gives us 192.2. To write that answer with 0 decimal places, with no decimal places, we would write it as just 192, right? So we add these together, and our final answer, 192 AMUs. That's the average atomic mass of any iridium atom out there in the universe. Now, you should notice that because our masses only had 3 significant figures, and our percentages had just 4, in the end, our answer isn't terribly precise. When you look at your periodic table, those little red average atomic masses in the upper right-hand corner of each value on our periodic table, we usually have a lot more precision than this. But we're following the rules of significant figures here, as we should, and we're going to stick with that as we're working through these problems. What you should do when you finish one of these, if you're calculating the average, as we've done here, you should go back to your periodic table and make sure that the answer you've got is somewhere close to the red value given on the periodic table, which serves in a lot of ways as a sort of an answer key. So let's skip back to that periodic table again and take a quick look here at iridium. And sure enough, right there in the upper right-hand corner, it tells us the average mass is 192.217 AMUs. That's the more precise version of the same work we just did. Now, you might ask yourself a question that isn't a terrible one to ask, and that is, if we already have the periodic table and all these average atomic masses, why do we bother to practice calculating these at all? And it's because we need to understand where those numbers come from, and that they represent sort of a weighted average of all the isotopes of an element's atoms out there in the universe. They don't represent any single atom. And that's an important thing to remember. There are no iridiums in the known universe with a mass of 192, or more precisely on our periodic table, with a mass of 192.217 AMUs. There is no such iridium atom out there in the world. Just like I said with your quiz, there's no such score as an 8.3 if that's the class average on a quiz. But it represents a big picture of many small pieces put together. And when we're working with elements in the classroom and in chemical reactions and in math of chemistry, we need to be able to use an average mass for a sample of iridium atoms, which we would assume in that sample, each iridium atom contains or has a mass of 192.217 AMUs according to our periodic table and the work that we just did. So that confirms sort of the work that's leading us to the periodic table, which we often just take on blind faith and never really think about critically where these numbers come from. It's important that we know where we're getting these numbers and sort of why they are, what they're based upon. Well, there's a second type of average atomic mass problem that I'll go through with you on the next video. Until then, hang on to this example and we'll work on the other ones on this page like it there in class.